In this video, we will discuss the solution to problem F from Atcoder Beginner Contest 333. Make sure to attempt the problem before watching the video. A quick overview of the problem is n people are standing in a line from front to back, and in each operation we pick the person that is standing in front of the queue, right? And with a probability of half, either that person is eliminated, so that is why you do not see that red box over here, or with a probability of half, that person is sent to the back of the queue. And once that person is sent to the back of the queue, or if he has been eliminated, we have a new configuration of people. So we will repeat that same operation on this new configuration, and we will keep doing the process until we have just one single person standing. So the problem asks you to find the probability that this particular ith person is the last person standing. So in this video, we will discuss some approach to this particular problem. But before we do that, let us go through a simple example to make sure that you understand the context of the problem. So now consider a line consisting of just two people, right? Person A and person B, right? And what if I ask you to find the probability that person A is the last person standing? So in the first operation, with a probability of half, you will eliminate person A from the game, or with a probability of half, person A will go back to the end of the queue, right? And the configuration becomes BA. Now after that, right, in this second round, the operation will be performed on person B. So either person B will be eliminated, leaving A to be the winner, or person B will go back to the end of the queue, right? And the new configuration will be A comma B. So if I denote P of A as the probability of A being the winner, then you can see that on every path, right, on every path that A is the winner, we need to sum up the probabilities, right? And on a single path, all the probabilities would be multiplied because all of these events are independent, right? So this is kind of a prerequisite to the problem, that you understand how basic probability works, right, with multiple experiments. Like if they are independent, they will be multiplied along the way. So for example, if you call it as probability of A being the winner, so you can see that if you go this route, then after this the probability of A being the winner is 0, right, because A has been eliminated from the game. So probability of A would be half into 0 for this route, and for this route it would be half into whatever follows, right? So in this area, A will definitely be the winner, right? So that is why half into 1. And in this area, after you arrive at this particular location, you will see that this configuration is equal to this configuration. So that is why if you called the probability of A being the winner from this configuration as P of A, then if you reach this configuration again, you are interested in what is P of A, right? So you have this particular equation. So if you solve this, you will get P of A as 1 by 3. So P of A was repeated on the left hand side as well as the right hand side, because this process is not finite, right? It can take a long time before all of the persons except one are eliminated from the game. So this is one method using which we concluded that if there are two persons playing the game, then the probability of the first person being the winner is 1 over 3, right? Now let us find out the probability of the second person being the winner. So for the second person being the winner, you can be smart and say that if the probability of first person being the winner is 1 out of 3, then of course the probability of second person being the winner is what? 1 minus 1 over 3, right? Which is 2 by 3, and which is correct, right? Because uh, both of these events are disjoint and exhaustive. So you can say that probability of B is equal to 2 by 3. But let us still calculate the probability of B being the winner in a naive manner. So for example, we start with this particular experiment again, and we say that there are two persons playing the game. In the first round, A will be eliminated with probability half, or A will be sent to the back of the queue. Then in the second round, either B will be eliminated completely or they'll go back to the queue. So if you write the equation, you will see that if the probability of B being the winner is P of B, then on this route B is definitely the winner, right? Because A has been eliminated. So that would be half into 1. And on this route, here B will definitely lose on this route, right? So that would be half into 0, right? Because B has been eliminated. And once it reaches here, you will see that the configuration is repeated. So you say half into P of B. So if you solve this equation, you will conclude that probability of B being the winner is 2 out of 3. So this was a second method to find the probability of B being the winner, right? The first method is of course finding the complement of P of A, right? But now let us look at a third technique that will eventually help us solve the original problem as well. And this technique is for computing P of B smartly, right? So if you observe this slide, we processed two rounds, right? On round 1 we inspected what would happen, and then we added the possibilities for round 2 as well, right? But if you notice closely over here, on the first round either A is eliminated and B becomes the winner, or the configuration reaches B of B comma A. But you do not need to expand this further, because you are now interested in what is the probability of the person who is standing at the front of the queue to be the winner, right? And since we had already computed P of A is equal to 1 by 3, it means that if you have this particular configuration, then the probability of B being the winner from here onwards is 1 over 3. So you don't need to expand this branches, right? You can simply say that on this route B definitely wins, so that is why half into 1, and on this route B will win with the probability of the first person being the winner, right? So that is why we had already computed that, so we plug it over here. So this gives us a basic idea that the identity of the persons in a queue does not matter, right? So it does not matter who we are calling A or who we are calling B, right? All that it matters is how many persons are standing to the left of the interested candidate and to the right of the interested candidate. So let us now define a function dpij. So previously we had seen that if you just focus on the number of people standing to the left and the number of people standing to the right, you should be able to compute the answer without worrying about the identity of the specific people, right? So this prompts us for a this prompts the question that what is the winning probability for a candidate for whom I people are standing to the left and j people are standing to the right, right? So we are interested in the general question that what is the winning probability for this particular candidate. So formally we define it as dp of ij is the probability that the person who has I people to the left, right, these I people, and j people to the right is the last one standing, right? So this is the general question. Now of course notice that we have just formalized the problem, right? Like answering these queries is still not an easy task, right? But if we were to get the answer of these queries somehow, we should be able to solve the problem, right? So what we can do is, since we do not know the answer to any of them, right, like we do not know the answer for, let's say, dp2 comma 3 or dp 5 comma 7, let us pretend that there is a black box that can answer all of these questions for you, right? So for example, you might have solved binary search on answer problems, right, wherein finding out the answer is a difficult task, but verifying whether an answer can possibly be correct, that is a usually easier task, right? So similarly, let us assume that you have a black box and you do not know how it works, right? All you can do is you can pass in some values I comma j and it will give you the answer to I comma j, right? And by answer to I comma j we mean that it will give you the dpij value for the particular indexes requested, right? So if you have this particular black box, right, that can answer all your queries for dpij, right, you can ask the value for dp2 comma 3, it will give you the correct answer. You can ask the value of dp5 comma 7, it will give you the correct answer, right? So if you have this particular black box, how do you check the consistency of this particular black box, right? So similar to binary search on answer, wherein finding the answer is difficult, but you can at least verify that whether the particular candidate is one of the answers or not, right? If it can indeed be the answer or not. So what are the possible checks that you can do on the output of this particular black box to make sure that it is spitting out the truth? So for example, one check could be that if dp of ij, right, if dp of ij, if it turns out to be greater than 1, you then know that the particular black box is not printing the truth, because no probability can be greater than 1, right? So that is one of the checks that we could apply. So how do we verify the consistency? By looking at other methods, right? So one is of course ensuring that dp of ij is less than or equal to 1. So let us focus on dp of ij, right? Like let's say if you want to compute the value of dp of I comma j, and you already have the answer from that black box, right? Remember that it can give you the answer for dp I comma j, but you just need to verify whether it is possibly correct or not, right? So if you have this configuration, then if you have this configuration, right, so if you have this configuration wherein I people are standing over here, candidate is standing over here, and then j people are standing at the back, right? So there can be two choices, right? Either the first person, like either the person that was here, either they get eliminated, right? In that case, you are now interested in dp I minus 1 and j, right? Because after this person is eliminated, we want the answer for the candidate being the winner when there are I minus 1 person to the left and j person to the right, right? And this particular value can of course be read from the dp table, right? Assuming that the black box can answer all the entries in the dp table. So this will happen with a probability of half. Similarly, the person at the front, right? If the person was at the front, they can be moved to the back of the queue, right? So that is why one person was removed, so that's why I minus 1, and one person was added to the back of the queue, so that would be j plus 1. So with probability half, the person standing at the front of the queue will be moved to the back of the queue, right? So now we are interested in the answer for dp I minus 1 and j plus 1. So if you remember, the n is equal to 2 case, right? So what we did was we performed both of these operations, and we said that the probability of a would be the combination of this branch and this branch, right? So we can apply a similar logic over here as well. Here we can say that dp of I comma j would be I minus 1 comma j with a probability of half, and I minus 1 comma j plus 1, right? So I minus 1 means person being eliminated but not being sent to the back, and I minus 1 means person being removed from the front but being sent to the back. So if all the answers from the black box, right, like if you store them in a matrix, and all the answers, all the particular cells in that matrix should satisfy this particular condition. So we have concluded that every cell of the dp matrix should satisfy this particular formula. But note that we haven't computed all of these cells explicitly, right? We are just assuming that there would be a black box which would be able to produce all these cells in O of one time, right? We just need to verify that the result is consistent. And also notice that even though we have named our matrix as dp, to understand all of these concepts you do not require intricate knowledge of dynamic programming, right? Like you can understand it even if you haven't solved any dynamic programming problem before. This is because we are not relying on any of the overlapping subproblems or any other techniques from dp, right? You can visualize, for now you can just assume that somehow all the cells in that matrix have been populated. You just need to verify the consistency, right? And of course you can do that by making sure that each cell in that matrix satisfies this particular formula. Now let's talk about how do you so if you apply this particular formula on each cell, then you can see that every I comma j will rely on the value of I minus 1 comma j, right? So look at it in space, right? Now let us forget about the context of the problem and let us just focus on this mathematical formula that you see on the screen. So if you have a point in space I comma j, if you have this particular cell, you can see that it only relies on this cell I minus 1 which is right on top, and j, right, which is right on top, and I minus 1 comma j plus 1, right, which would be the element on the anti-diagonal, this one and this one. So for each cell you need to verify whether it is a combination of this cell and this cell, right? So now it begs the question that if we are able to do such a verification easily, right? Like if you can just travel through all of these cells and verify that this particular formula is satisfied, can we also compute all of these values by on our own instead of relying on the uh, magic box that we have, right? On that black box that we have that used to produce the answer. So you can see that this particular cell depends on this cell and this cell. So if you notice, right, like if I give you the answer to the first row of the matrix, then you can compute the answer for this, right? Because you already have the formula, you know that this is a combination of this plus this, right? So since the first row was available, you should be able to fill this. In fact, you should be able to fill any of the value on the second row, right? Because any of the value on the second row would depend on only the values on the first row, right? This one and this one, right? This one and this one. So if you have the first row somehow populated, then you should be able to fill all of the remaining rows as well. So all that is fine, but there is still a challenge remaining, that is finding out the answer to the first row cannot be done easily, right? But let us come back to that later. Let us first focus on solving the sub problem, right? Like solving the easier version of the problem, which is that if the first row has been populated, can you populate all the other DP rows, right? And the answer is yes, because you can start from left to right, and every time you want to fill an element, the element to the on the top and on the anti-diagonal will always be present correctly. So you can just fill all of these elements in this order and it should work. So what will the answer be for the original problem, right? So the original problem was to find the probability that the ith person is the winner, right? So you can look it in DP terms, right? Like how do you retrieve it from the matrix? So if the ith person is the winner, then initially I minus 1 people were standing to the left of that person and n minus I people were standing to the right. So the DP I minus 1 comma n minus I would represent the answer for the ith person being the winner, right? So we can just read it off the DP table and print the answer. So it is clear that once you have computed the DP table somehow, you should be able to answer the original question as well. And it is also clear that if you have the first row of the DP table already populated, then it should be pretty easy to figure out how to compute the rest of the rows. Now let us focus on the first row, right? So in the first row, we know that I would be 0, right? Which means that there are 0 persons standing to the left of the candidate and j person standing to the right. So in one operation with probability half, either our candidate can get eliminated from the game or they can move to the back of the queue with probability half. So you can clearly see that DP 0 comma j would be half into 0, the person is eliminated, plus half into DP j comma 0. And of course, if you look at the first entry in the matrix, that would be DP 0 comma 0. And by definition, DP 0 comma 0 is the answer when there are 0 persons to the left of the candidate and 0 person to the right. So of course the winning probability is 1 because there is just one person standing. So we have this relation for the first row, right? But now here is a challenge. You can see that this was 0 comma j, right? And this was j comma 0. So this is now depending on this. And we have previously seen that this depends on top right. This depends on the element on top and the anti-diagonal ones, right? So this also indirectly depends on this. So it is not an easy task to compute all of these values, right? Because this depends on this and this depends on this. So essentially there is a cycle in the transitions, right? And rightly so, because if you remember, for n is equal to 2 case, we had x on the left hand side and x also on the right hand side, because this was not a finite experiment, and it was possible to retrieve the same configuration again, right, after some number of steps. So, and that makes sense, right? That is why this depends on this and this in fact depends on this. So instead of worrying about all of the values that can change or that can depend upon each other, let us start focusing on the cells one by one. So of course this is dp 0 0 and we know that this is 1, right? And we have also seen that elements which are mostly dependent on each other, they lie on the anti-diagonal, right? So now let us consider the first anti-diagonal, right? Like let's consider the next anti-diagonal, which is this. So this is of course 0 comma 1 and this is 1 comma 0, right? So if you assume this value as x, right, if you assume this value as x, this value would be what? This would be half into 1 plus half into x, right? So that is why dp of 1 comma 0 is half into 1 plus x by 2, right? Which is what we determined, that any cell can be written as a contribution of the cell on top and on this and the cell on the anti-diagonal, right? And we also determined that this is equal to this by 2, right, on the far end of the anti-diagonal by 2. So we have the equation that 2 of x is equals to half plus x by 2, and we can see that x is equal to 1 by 3 as we determined in this sample problem as well, right? So we add this value 1 by 3 and 2 by 3 on this anti-diagonal. Now let's focus on the next anti-diagonal, right? All the elements that are on this anti-diagonal. So keep in mind that we have correctly filled the value of this and this, right? So how do we correctly fill all of the values over here? So if you assume this to be x, this will naturally be half into x plus half into 1 by 3. Then this would be half into 2 by 3 plus half into whatever is present over here. So half into whatever is present over here, we write it over here, right? And there is also a relation between this and this, right? And the relation was that 2x is equal to this, right? So if you plug x over here, you should be able to find the answer for this. So we were able to notice two things, right? One is that if you fill the dp table in the anti-diagonal order, right, like first you fill these set of elements, then you fill these set of elements, then you fill these sets of elements, and so on, then by the time you reach any anti-diagonal, you can guarantee that all the elements on the upper triangular matrix are correct, right? That much you can guarantee. Also notice another thing, that if this is x, then this is either scaling of this or constant addition of this, right? So basically this is a linear function in x. So if this is the linear function in x, this will also be a linear function in x, right? So that is why all of these are linear functions, right? This. So that is why you will be able to get a relation from here to here. So you can notice that if you start with this, you can write it as a linear function as 1 into x plus 0. Then this cell would be what? Half into this plus half into this, right? So half into this, right? So you are multiplying something to a linear function, of course it will stay a linear function. Then you are adding something to a linear function, it will of course stay a linear function, right? Similarly, this will be a linear function of x, and you can compare it with 2 of x, 2 into x, right? The relation that we derived earlier. So you notice that at each step, right, if here you have ax plus b, then here you will have p into ax plus b. So at each step the coefficient of x gets multiplied by half, right? This contribution and this contribution, and then the constant term also gets multiplied by half, plus c1 by 2 gets introduced, right? So since each of this is a linear function in x, it might not be easy to store it in a computer, but if you notice that any linear function can be written as ax plus b, right? Any linear function can be written as ax plus b, right? So if you have ax plus b, then on a computer you can simply store the pair a comma b, or two variables representing a comma b, and if you need to scale the linear function, you can simply do 2 into a comma 2 into b. If you need to add a constant to that linear function, you can simply do a comma b plus whatever constant that you want to add, right? So if at any stage, you had a linear function with a comma b, this will again be a linear function with a prime comma b prime, this will be a linear function with a star comma b star, and finally you will get this particular relation, right? dp0 comma j is half of dp j comma 0, and this will of course be a linear function, and the left side is 2 into x, so you can derive that x is equal to b by 2 minus a, right? And here a and b represents the coefficient of the linear function for the cell on the farthest end of the antidiagonal, right? This particular cell. So you will be able to retrieve the value of x if you start from here and then propagate the linear function all the way down, right? And once you have the value of x, you can again start from here and then pass down the information. So this will ensure that this particular anti-diagonal is filled correctly. So now you can see that just with this particular formula, right, and without really relying on a lot of background knowledge, we concluded that any matrix that satisfies uh, the queries of the that has the queries of that black box should satisfy this formula for it to be consistent. But then if verification was so simple, then creation of this particular matrix should also be simple, right? So here you can see that I belongs to I depends on I minus 1 j, right? So this blank depends on this and this, or this depends on this and this. So if you start filling all of these cells in an anti-diagonal order, right, wherein you fill this first, then this, then this, then this, then you will ensure that when you are filling this particular anti-diagonal, the largest anti-diagonal, then you require the value of this, right? Of course you will have this value already computed. Similarly, when you are filling this, make sure that you have already filled these anti-diagonals, right? So the idea is to we know that this will be dp0 comma 0 would be 1, and then you assume this to be x, or assume it to be a linear function of x, which is 1 into x plus 0, then this is also linear function of x, and then you have another relation between these two, right? So you compare them and find the value of x, and then you propagate this result down. Then you start from here, you assume it to be x, this would be x into p, right? From this formula, this would be x into p plus half in plus p into whatever you have already computed and placed over here, right? So you add this linear function over here, then you do the same for this, right? Then similarly you start for this and you proceed down. Now let us look at the implementation for this particular idea. So you can see that I defined dp I comma j as the number of, as the winning probability when there are I people to the left of the candidate and j people to the right of the candidate, right? And then we start from each anti-diagonal, right? So the smallest anti-diagonal is 0 plus 0 is 1, so this one is already computed. Then this is 1 plus 0, right? So the property of anti-diagonals is that x plus y remains constant on that anti-diagonal, right? So this would be 1 plus 0, so that is why I start from 1 and it will go till 3 plus 0, right? So that would be n. And at each step we keep the a comma b of that linear function, right? So this is x, which means 1 comma 0, right? 1 into x plus 0. So we start with x plus 0, and at each cell that linear function will be transformed, and the transformation would be that multiply the coefficient by p, which is half. So that is why x becomes p into x, and the coefficient becomes coefficient into p plus an addition of a new coefficient, right, which is the cell right on top of it, right? And then you go down on that anti-diagonal. After you are done on the last cell, you already have a relation, and we already derived that x would be b by 2 minus a, and where a and b are the coefficient of the linear function on the last cell, right? So we apply this formula over here, and then we backtrack on that diagonal, and then we populate all of these value, right? Once that is populated, we will make sure that this anti-diagonal is populated, and then we can move on to the next anti-diagonal, right? So, and at the end we print dp I minus 1 comma n minus I. And for the time complexity of the solution, you can notice that we have an n cross n grid, and all we are doing is we are traversing each anti-diagonal twice, right? So we are doing no more than O of n square operation, which is the time complexity of this program.